All right, you guys, let's continue our talk about exponential models by looking at the following problem. So it says the size p of a certain insect population at time t in days obeys the function p of t equals 500 e to the 0.09 t power. So A says determine the number of insects at t equals 0 days. Okay, so the first thing we're going to do is we're going to look at our function that they gave us. So the function, the exponential function that we have is p of t equals 500 e to the 0.09 t power. Okay, so if we recall, any exponential model will be set up in this form. A of t equals a naught e to the k t. And from this model, we know that a naught represents our original amount. We know that k is equal to our growth factor, and t is equal to time. Okay, so the first thing that we know that this is a growth model, and we know that because k is greater than 0. So we know we're dealing with a growth model. Okay, and A says determine the number of insects at t equals 0 days. Well, at t equals 0 days, that would be at the present time, like what's going on right now. So that would mean that would be our original amount. So as we look at this function, our original amount is 500. It's sitting in the A naught position, which tells us the original amount. So we have 500 insects when time equals 0 days. Okay, let's look at B. B says, what is the growth rate of the insect population? Well, our growth factor is always what k is, okay? And k is represented by a percentage here, is what they want. So our k is equal to 0.09. Now, if we change that decimal to a percent, it would be the same thing as multiplying it by 100. So 0.09 is equivalent to 9%. Okay, let's look at C. C says, what is the population after 10 days? Okay, so 10 days is our time. So they want to know, another way is what is P when t equals 10? Well, we have our function already. We can simply plug that into our function. So we can say P of 10 equals 500 e times 0.09 times 10. And we can simply put that into our calculator. When we do that, we end up with this, 1,229.8. Okay, and our directions say to round to the nearest whole number. Well, if we round 1,229.8 to the nearest whole number, it's going to be 1,230. So we're going to have approximately 1,230 insects. Okay. All right, let's look at D. So D says, when will the insect population reach 800? Okay. So in that question, another way of saying that is what is the time when P equals 800? Well, once again, they gave us our function, so I can simply plug in 800 in for P. So I have 800 equals 500 e to the 0.09 t power, and I need to solve for t. Well, the first thing I'm going to do is I'm going to divide both sides of my equation by 500. So it's going to give me 800 over 500 equals e 0.09 t. Now at this point we have an exponential function, okay, an exponential equation, and I know this because my variable is in the exponent, which is the t. Now remember, because this is an exponential equation, the only way I can get that power down is if I can get the bases on both sides of my equation to be the same. In this scenario, I can't. So remember, what you can do, you can take the natural log of both sides. Okay? When I do that, by the properties of logs, the natural log of e cancels. It goes to 1 because they're inverses. So that leaves me with the natural log of 800 divided by 500 equals 0.09 t. The power drops down. Now I can solve for t by dividing both sides of my equation by 0.09. So t equals the natural log of 800 over 500 divided by 0.09. Now, let me see how they want their answer. So as I read my instructions, it says do not round until the final answer and then round to the nearest tenth as needed. Okay, well, I haven't done anything, I haven't simplified, so let me plug this into the calculator. When I do that, I end up with this. So I plugged in natural log of 800 divided by 500 divided by 0.09, and I get 5.22226. Okay, and it said round to the nearest tenth. Well, to the nearest tenth is to 1 decimal place, so that's 5.2. So in 5.2 days, my insect population should be at 800. Okay, and then let's look at E. So E says, when will the insect population double? Okay, so another way to think about that is question, what is T when P is doubled? Well, in order to know how much population is when it's doubled, we would have to know how much it is at the start. Well, we do know that. Remember, we started out with 500 insects. That was our original amount. So if we were to double 500, okay, doubling 500 equals 1,000. So really what they're interested in is what is the time when population equals 1,000. Okay, so we can set this up similar to how we did part D. Okay, so let's move over here. So I'm going to set my equation. So I have 1,000 equals 500 e to the 0.09 t, and I'm going to solve this equation. So the first thing I'm going to do is divide both sides by 500. So it's going to give me 1,000 divided by 500, okay, equals e to the 0.09 t. Once again, this is an exponential function again, so the only way that variable can come down is if I can get the bases to be the same on both sides. I can't, but I can take the natural log of both sides. When I take the natural log of e, they cancel. That simplifies to 1. So I'm left with the natural log of 1,000 over 500 equals 0.09 t. And I need to solve for t, so I'm going to divide both sides of my equation by 0.09. So t is equal to the natural log of 1,000 divided by 500 all over 0.09. And once again, I can plug this into the calculator and see what I get for that one. When I plug that into the calculator, I get 7.7016, and my directions say to round to the nearest tenth as needed. So the nearest tenth would be to 1 decimal place. So that would be 7.7. Okay. Cool. So make sure you pay attention to the directions. that you put the answers in the way that they've asked for them, and just be careful not to round until the end. So use your calculator to put in your entire expression, and then round your answers at the end. Cool.